morning. Well, it's a pleasure to be here. My name is Jan. I live in the Bay Area, and I've been fascinated with just how quickly machines are getting smart. And about a year ago, I started a company to write open source software to help other people make their machines smart as well.
Nice. And when you say smart, how would you define smart in that sense?
Yeah, that's a big
Oh,
question there. That's a whole spectrum of
right.
possibility.
Well, we typically think about machines as being relatively inert. We program them, we tell them exactly what we want them to do, and we don't expect them to have engaging conversations or make decisions on their own or learn and change. And all of that is now possible. It turns out that all the things you've been hearing about with chatbots and AI and large language models, those are not only important for coding and not only important to help my students do their engineering problem sets, but it turns out that many of those large language models also speak fluent robotics. And that means that there is now a very clear path towards machines that learn, engage, smile, have conversations, remember, work with other machines to become much more like people and teachers and coworkers.
So what are the barriers of entry there? Are you working with existing LLMs and making them and giving them more intense training in order to make them more human-like or smart? Or are you building things from the ground up? Or is it far more like analog and you're building IoT stuff to make machines more interactive with the world around them?
Oh, um, given how quickly large language models are improving, it wouldn't be wise for us to try to build our own language model or our own foundational model. What we've realized is that we're able to put together, like Lego blocks, models that other people are building to make sense of vision and speech and the physical world. And by assembling those pieces, we don't have to spend a lot of time on each individual model. We can focus on how to integrate those models into software that make it easy to, for example, add and remove functionality and so forth. For this kind of approach, the really important part is to come up with a good system for having data about the world come together into a unified model for your environment. And then those data feed into combinations of large language models that then create the emotions and the responses and the decisions.
Wow. Very cool.
So the building blocks of the future. I'm sure you get the Skynet joke all the time. Just as soon as you said emotions, then I'm thinking of the anger one.
Going down.
Sure. Well, I think many people in sort of engineering or technology, when they think about something like all machines being connected to all other machines, that has clear technical benefits, sure, and it allows machines to do really interesting things. Like once one machine has learned something, it can transmit that information and that skill to all other machines. Um, so from a technical perspective, of course, that sounds really exciting. But if you are a simple human, then it also brings with it considerable sort of risk. And I hope that everyone who's working on this kind of technology is also thinking ahead a little bit in terms of how humans interact with machines and how to give humans confidence and trust that those machines will do the right things and not harm them and so forth. That's, of course, been a big conversation area in science fiction for many decades. Certainly, Isaac Asimov's laws of robotics immediately come to mind. And so the good news is that we don't have to start from scratch.
You beat me to it there. That was my next kind of obvious question. I was hesitating to bring up, but how closely do you work in that? I mean, it's a science fiction specifically a work of fiction, but how close does it play to reality?
Well, the science fiction that you read about as a kid is currently being built and deployed. So it's no longer science fiction. Multiple companies are thinking along these lines. One great example is Anthropic, that's been emphasizing this notion of a constitutional AI. Another example is Google with their new Gemini Robotics, which has Asimov's laws of robotics baked into the model. And we certainly are deeply supportive of that kind of thinking. It's not just that we want to make machines smart, we want to make machines trusted and good and honest and predictable companions and partners and mentors. Um, of course, it's not so easy because, as Isaac Asimov has already pointed out, just because you have a few simple rules doesn't mean things can go well. Another example would be A Space Odyssey, 2001. Remember how HAL, the computer, decides that to execute the task, humans are actually standing in the way of mission success, and then comes up with this scheme to eliminate barriers to mission success. So there's certainly many fascinating situations where just because I have a simple set of rules, it doesn't necessarily mean that everything will go well.
It reminds me a little bit of the AI in Ex Machina as well. You know, the Ava unit that kills her creator to get to sort of like the complete mission success as well.
I mean, it's absolutely fascinating that what you're describing here, playing, having a set of rules and then seeing how situations play out in unpredictable ways. But the idea, I suppose, is to narrow that eventuality to make them more predictable and as safe as possible over time.
Well, absolutely. I mean, there's no certainty here, and humans have been developing rules for thousands of years, and we call them laws. But of course, many humans struggle to stick to laws, and that's why we have courts and judges, and police and jails, and social expectations. And so humans, of course, are generally extremely bad at following laws. And human societies have had to build out this entire infrastructure to deal with situations where humans don't follow the rules. I think I have like 8 unpaid parking tickets right now in San Francisco. So I certainly struggle with following the rules as well. And I'm sure many listeners can think of at least one situation where they also, struggled a little bit. So this problem is not only a machine or robot problem. This is a problem that all humans are very familiar with as well.
Interesting. And as part of your work, you also teach at Stanford, is that right?
Yes.
Do you find that, this is a bit of a leading question, but do you find that your work with robotics and in this field kind of overlap with the teaching that you do, and does one inform the other?
Well, yeah. Generally, teaching is very useful because when you teach, you have to first understand what you're trying to teach, and it forces you to you can't really cut any corners there. But what I see in the teaching world or sort of university world is that there's a massive change underway, and the massive change is that machines are getting smart. And that raises extremely basic questions about what a university should be doing. Universities, of course, are in the business of teaching humans. Should they also be in the business of teaching AIs? What does it mean to prepare humans for their future careers in a world where many careers are going to be significantly impacted by AI? A great example would be computer science. Just 5 years ago, for Stanford computer science graduates, it was very straightforward to get a high-paying job in computer science at one of the big tech companies around here, for example. But just in the last 2 years, that's changed very, very, very quickly. And this is only one of the areas that's being affected by AI. So by virtue of teaching and being at the university, I get to meet really interesting students who are going to go on to build tech companies and new technologies. But it also forces me to grapple with what does it mean for an AI to be trusted, and how shall humans interact with the technology.
Dive in a little bit to the actual tech that you're using. What languages are you writing in, or is it how much? What's the divide between software and hardware? Robotics building. How does it break down?
Well, the way we think about a robot is as a platform for motion and as a platform for collecting data. And those data can be images and sound and GPS data and Bluetooth packets and LiDAR data, just to give a few examples. And all those data then have to be turned into something that an AI understands. And then the AI that typically lives in the cloud can then make decisions based on a continuously updating synthesis of the world around them. There's a few exceptions to that model. For example, if you're dealing with underwater robots or military robots, you typically try to do a lot of the decision making directly on the device because you don't have access to the cloud. But for a typical sort of commercial or consumer application, the decisions are made in the cloud by existing large language models. These are things like Gemini or Claude or OpenAI or DeepSeek. And our role as we write software, we use mostly Python. Our role is to make it easy for people to add new data streams and then to make optimal use of the decisions coming back from the cloud, from the large language models, in terms of what additional data to collect, what movements to perform, and how to interact with the humans around the machine.
On that topic, I think this kind of dovetails a little bit into something else. So I remember listening to a Lex Friedman podcast a while ago. He was interviewing the CEO of Boston Dynamics, and he was saying one of the hardest things that they found was the overlapping of those discipline fields. So everything has to be a kind of state of the art. The mechanics and the the actual architecture of the robots themselves, and then building in the technology as well. You're not just working in one field. It's like many disciplinarians working across many fields, and managing those teams and making them mesh together is quite tricky. Is that something that you found as well?
Yeah, that's the biggest problem in robotics. That's one great example is one of the things I struggle with right now is the form factor of the American front door.
Okay.
Most of us have front doors that we have to wiggle a little bit and jiggle, and we need a key to unlock the front door. And just something as simple as a robot opening your front door is extremely complicated.
Well,
The
thank
first
thank
question,
God for.
yeah, and so for a robot, it is horribly difficult. It involves a very significant degree of manual dexterity. It involves fumbling with the key. And then related to that is a general question of which robots are allowed to unlock your front door. And that means that humans have to somehow authorize this. And then even if you've authorized a robot to open your front door, you still have to figure out how you prove that the machine in front of you is the robot that you authorized to open the door. So something as apparently simple as a humanoid unlocking your front door raises questions relating to like security, identity, authorization, mechanical characteristics of your door, exactly how you have to wiggle it to open it. How does the robot get access to a physical key? And right now, in fact, probably in the US, the biggest barrier to deploying humanoids to solve the last mile problem, which is defined as, a robot showing up at your door and you somehow get the food into your refrigerator. The biggest remaining problem is everything relating to your front door. Everything else at least
That's amazing.
has a reasonable way forward.
How much standardization is there across the industry then? Because I imagine 5 different companies competing with 5 different designs to solve the same fundamental problem is overall a negative to the rest of us as a
Talking about
consumer.
the front door industry.
No.
Well, the only reason for all the exuberance about humanoid is that if you're looking to introduce thinking machines into a human world, the closer the machine is to human form factor, dimensions, characteristics, and manual dexterity, the easier it is for the robot to navigate the human world. Probably the way this is going to play out is not that we're all going to have standardized front doors that are somehow humanoid compatible. The way this will play out is that humanoids are very quickly acquiring the manual dexterity to have similar performance to humans. And what that will mean is humanoids will seek to just be much better able to navigate this heterogeneity of front doors, for example. So yeah, I find it unlikely to imagine that we're all going to replace our front doors. Just the humanoid hands are just get better much quickly.
R2-D2 always seemed like an unlikely final design.
He never had a problem with the door, did he, R2?
But they're all automatic in space, right?
Yeah, there are no keys.
So you run hackathons as well. I think that's something that might be quite interesting for a lot of our listeners. Can you tell us a little bit about the ones that you do?
Sure. One thing that you find in robotics is that it can be extremely difficult to get started because it's not only about writing some code. Generally, you have to know about cameras and USB buses and serial ports and middleware and data formats and all the compute you have to do quickly so that your robot doesn't run into walls and things like that. And what we found is that for like a general undergraduate or high school student or a newcomer to robotics, the barriers to entry are very severe. You have to know a lot of things to be able to build a robot that does something interesting. And what we've been trying to do with our software, one of the reasons we use Python is to at least use a language that most people are familiar with. But we've also tried to build the system in such a way where newcomers have a fighting chance to figure out how to modify it and add new functionality. And that's part of why we use this Lego block approach. Another approach in the robotics world is to build single models that try to do everything. And these are called end-to-end AI or foundational models. The problem with those models is it can be very difficult to add new types of arms and legs and wings and wheels and new types of eyes and antennas and sensors simply because the unitary models, the foundation models, are really not designed for heterogeneous machines. You can certainly write software that is good at controlling a car, but just imagine the car suddenly acquires a wing or loses a wheel. How does the software accommodate that situation? And so a modular system that abstracts away things like the movement capabilities and the data collection capabilities is a little bit easier for people to deal with, but brings with it its own problems. But what we try to do is make it possible for a typical high school student or a university student to very quickly add new interesting functionality. And ideally, of course, humans wouldn't have to write computer code anymore anyway. You certainly would prefer to have a machine that you can have a conversation with. Dan, imagine you're a machine, which in some technical sense you are, and I'm able to tell you. I mean, unless you're powered by
No, no.
magic.
I've just been waiting for someone. I've been waiting for a professor to tell me that for many years. So now it's
No, I'm certainly. All of us are, physical objects navigating the physical world, and the three of us are able to learn and listen and change our behavior based on voice inputs, like this conversation we have right now. There's no need for us to be writing explicit computer code and sort of uploading the firmware to some machine. So the three of us are existence proofs for machines interacting and using voice to coordinate and to learn. And I certainly expect that to be true also of other machines that just happen to use a different compute platform.
And in terms of the actual the hackathons and how that sort of feeds back into it. So I remember you told me before when we caught it before we recorded an interesting story about how quickly people in these hackathons are actually able to put these blocks together and actually come up with solutions. Maybe you could give us a bit of insight into what the people did, because I was amazed at how far they got in the time they had.
Yeah. Well, that really speaks to the skills of the hackathon participants. Just one example, one student team put together a system where a robot uses video data and voice inputs to assess people with potential sort of Alzheimer's or Parkinson's disease, and then use that information to change how the robot was helping the human. And that's a little bit of a unusual capability for a humanoid to have. A prevailing focus in the robotics industry is still fine motor skills. There's this long-standing idea that what defines an amazing humanoid robot is its movement. Is it a ballerina? Can it tiptoe? Can it do a backflip? Can it navigate slippery surfaces? But the reality, of course, is that most humans are not ballerina dancers, and many of us, myself in particular, are very clumsy. And a lot of what makes humans interesting and useful to other humans is not necessarily their manual dexterity. These can be things like, how does this person listen? How do they engage? Are they funny? Do they remember what I said? Am I able to build a connection with this other human or machine? And what we've been emphasizing software-wise are really all these other capabilities that humans have.
like
the voice.
opening front doors.
It's with the exception of front doors, which of course that manual dexterity. But and so what we've been emphasizing in hackathons is really for kids and university students to add interesting, unexpected capabilities to humanoids. There's so many stories that I hear now about how people connect to machines. A great example would be that if you deploy humanoids into old people's homes, some of the people in, say, a memory care unit have not been visited by a relative in years. And a robot is able to listen and communicate and is able to make them laugh. And some people get so connected to the humanoid that the human nurses in the evening have to wipe lipstick off of the head of the humanoid. And you can look at these kind of situations and say, oh, this is like scary, creepy. This is some kind of dystopian future where our parents are kissing heads of humanoids because we don't visit them in the old people's home. But then again, I also see the perspective of someone who's in a memory care unit who hasn't been visited by a relative in years, and all of a sudden has something in front of them that listens to them, remembers what they said, and smiles and makes them laugh. And that they respond emotionally to that is not surprising to me.
I see very little downside in that. Yeah, that seems like a very positive, wholesome approach.
It's very interesting kind of crossover as well, isn't it? Because you also have the the robot that knows the person as well as they can, from the information that's been inputted into that robot, but also it has the other side of it, which could have all of the information that's been inputted into it via healthcare workers. Because I think that one of the most difficult things with memory care is the fact that family and relations get very frustrated with how their relatives can't be the same person they used to be. So they can often reply and act very frustrated with them, or not in the way that's best for the person who's in care. But a robot would basically know both sides of the coin, so it probably gives them a lot better care than either a human doctor or a human relative could.
Well, I think we have a lot to learn in that regard, but I couldn't agree more. There's many situations, if you look at interactions of family members that listen to the same story the 20th time or the 50th time or the 100th time, or you visit someone who doesn't realize that you're her son or daughter, and you have to explain again that that's your mom. And that certainly can be frustrating, can also be very difficult for family members. And we have a lot to learn in this regard, but just based on sort of practical, direct observation, it wouldn't surprise me at all if we see more and more building of deep connections and relationships of humans with machines. Another great example would be the current boom in the AI girlfriend industry. It turns out that having a digital girlfriend for some people can be quite quite addictive, and we should certainly foresee that in many areas, whether it comes to boyfriends or girlfriends or companions, mentors, teachers, and many other areas, where I wouldn't be surprised if humans develop quite deep and durable connections with machines.
Yeah, and that's another well-explored idea in science fiction, because it seems like a very foregone conclusion that of course they would. If someone can be a perfect partner with no mistakes, then that's very appealing, at least on the surface. At least on the surface, until you realize that mistakes are kind of the point.
Well, that is why advanced AI girlfriends, or also humanoid robots, deliberately make mistakes.
No, we're doomed. We're all doomed.
No. So, for example, if we program a quadruped dog to help you move your groceries around, if the quadruped dog does that perfectly, humans think that's kind of creepy. But if the quadruped dog occasionally drops something on the floor, humans are very familiar with dropping things on the floor, and they'll come running and they'll put the tomato back on the little basket on the back of the quadruped dog and say, "Oh, Bits, no problem. Let me help you." And exactly, one of the quadruped dogs we're testing out in supermarkets is called Bits. And so you deliberately want to have the system not be perfect, because that helps you build these deep emotional connections with humans.
It's interesting on that topic, actually. I was listening to something the other day, which the example the person gave, they said that, do you feel more emotionally connected to a rock, or a rock with a smiley face drawn onto it? And do you pair that with that piece of that I think it's a statistic that the thing that women want from a man is someone to make them laugh, and what men want more than anything in a relationship is someone to laugh at them or with them. So you can combine those two pieces of information, and you kind of throw a character AI into the mix, and it's just, you're right, it's just like, it's almost a no-brainer. It's just
a rock that laughs at all your jokes.
Yeah, a rock that laughs at my jokes. That's all I want in my life.
Okay, look, we're nearing the end, but I do have a quite an important question. Given your position as an educator and your position in robotics, what kind of skills do you think a lot of newcomers into tech, specifically our listeners, for example, it's changing so much. You said yourself that the ability to write code isn't necessarily as important as it was. So what skills should people be focusing on now And before you answer, I know that it's a moving target and it's always going to change. But to the best of your knowledge, what kind of things should people be focusing on now? Core skills?
Well, the only thing I see is that many people that are currently successful um, in various industries tend to spend a lot of time learning new skills continuously. So this old notion that you go to university, you get a degree in fill in the blank, and you then do that for the rest of your career, that is over completely. And one thing that seems very important is recognizing that the kind of things you will be doing as a human over the next few years and decades are likely to be subject to very rapid change. And the more you're able to be nimble and learn new skills and pay attention to what's going on, the better you will be able to navigate the future. So I don't have a specific recommendation of, don't become a radiologist. That's solved. That would be silly. But my recommendation would be to approach your education and job and future with a perspective of extreme nimbleness, that you should expect the world around you to change very, very quickly. And the faster you're able to learn new skills, the better off you're going to be.